Thank you for the introduction. My name is José Alonso. I'm R&D advisor and co-founder of Indicen Optical Technology, IOT for short. And I'm going to talk about our latest core lens design technology, which is called IOT Digital Raypath 2. The outline of the presentation is this one. We will go very fast through a few concepts of lens design, then the two main features of the new technology, the accommodative object space and the physiological compensation of oblique aberrations, and we'll finish with results and conclusions. Lens design. Lens aberrations, lenses have aberrations. It's easy to make a lens and adjust the curvature of the surfaces in such a way that the retinal image of an object is sharp, but just for one viewing direction, typically the main viewing direction with the visual axis horizontal. But when the eye rotates, the lens has an effective different power, and then the retinal image gets blurred. Okay, this is the main problem affecting ophthalmic lenses, and this is what we call oblique aberrations. In general, when we optimize a lens, what we're trying to do is to reduce these oblique aberrations, and we do that, or we intend to do that, for the whole field of view. That means for all the possible viewing directions available within the frame. So, for example, for this direction upwards, this direction downwards, and for each viewing direction, we have a predefined object distance. Because as we will see later, the oblique aberrations of the lens will depend on the object distance. Then typically we will have this green curve representing the object distance associated to each gaze or to each viewing direction. Then how our standard optimization technology has been working all this time. We just create a model of the lens and the eye. We use personalized personalization parameters to create this model to determine the right position of the lens with respect to the eye and some eye parameters. And then once we have this information and we assign an object distance to each gaze, then we aspherize the back surface of the lens by an optimization process. And in this way, we can reduce the blur of the retinal image a lot. But the problem is that no matter how the optimization is made, there is no surface that will restore completely the sharpness of the image for all gaze direction. We can reduce the oblique aberration, but we cannot eliminate all of them. Surface geometry is not enough. In that sense, we can extend this technology we've been using for the last years, using the ability of the eye to accommodate, accommodation. Accommodation basically is the capacity of the eye to focus objects at different distances by changing the power of the inner lens of the eye that we call the crystalline lens. For near objects, the crystalline lens gets thicker, it has more power and allow us to focus near objects. The maximum accommodation that we can exert, that the eye can exert, is called amplitude of accommodation. And this amplitude of accommodation dwindles over time. It gets smaller as we get older. Above 40 years of age, we enter a condition that is called presbyopia, in which accommodation is not enough to focus near objects for reading, for example, and then we need an external eye, typically what we call addition, on the lens in order to perform visual tasks at near distances. Addition, accommodation, amplitude of accommodation approaches zero, but not quite. For the elderly, it stabilizes at some value that we call an effective accommodation, that depends on the optical properties of the eye and physiological properties of the eye, and it's about 0.75 diopters. And this is the value that will harness to improve and further reduce the oblique aberrations of the lenses. And then this is the way IOT digital ray path 2 works, making full use of accommodation in lens optimization. And there are two ways in which we use accommodation. The first one is using the accommodative object space that we will define next, and then using a physiological compensation of oblique aberration, a compensation that will use accommodation. Let's see first the accommodative object space. The object space in traditional lens optimization is like this. There are two types. What we call the fixed object space that we can see here at any gaze direction, up, center, down, whatever. We are assuming that all the objects are at the same distance. For example, here at infinity, but it could be any other closer distance. So this plane in which all the points, the object points are located, is our fixed object space. For progressive lenses, we typically use a variable object space in which the assumed distance of the object changes with the gaze, but still for any gaze, we have a unique object distance. This is what digital ray path has been doing all this time. Now, what we are going to do is to consider that for each gaze, we have the typical accommodation level, the typical object distance, but then we have a range of object points that we can bring into a perfect focus through accommodation. Instead of being a simple point, it's a segment. And then for different gazes, we have a different segment. For example, for near vision, we have this point corresponding or this object distance corresponding to the more probable accommodation level. But if we increase accommodation, we will be able to focus closer objects. And if we relax accommodation, we will focus objects located further away. So what we are going to consider in digital ray path 2 is not just this green surface, but the whole volume formed by all these segments as we consider them through all the gaze direction. This blue region is what we call the accommodative object space, and is all the points inside it are considered when a lens is optimized within the IoT digital ray path 2 environment. Let's see now the physiological compensation of oblique aberrations. There are two main components of oblique aberrations, cylindrical and spherical. The cylindrical power error is characterized by having a blur patch in the retina, which is elliptical. Then, for example, if the main axis of the ellipse in the retina is horizontal, we will see horizontal lines as focused, while vertical lines will be clearly blurred. Okay, this is a typical characteristic of cylindrical power errors. But the spherical power errors will produce circular blur patches on the retina. So the blurring is isotropic. Okay. The point is that accommodation is an increase or a reduction of the eye power, spherical eye power. So we can think that accommodation will be able to compensate, at least to some extent, the spherical power error. It won't compensate the cylindrical power error, but will compensate the spherical one. And this is the difference, the main difference between DRP and DRP2, what we call the physiological compensation. DRP will try to make the blur patch on the retina with the smallest possible area. DRP doesn't care if there is some astigmatism. It will try to reduce the area as much as possible. Okay. Instead, DRP2 will try to remove the cylindrical component as much as possible. If necessary, it will leave some round blur patch corresponding to spherical oblique power. But the question or the point here is that accommodation will be able to remove this, excess spherical error. So in order to remove the oblique power, we will use the two things. On the one hand, DRP2 will aspherize the lens to remove oblique astigmatism, and we count on the eye to remove the remaining spherical oblique aberration. Let's see the results that we obtain with this technology. Let's consider a lens, and all these green points here represent different gazes or viewing directions. Each point represents the intersection between the gaze direction and the back surface of the lens. At each point, the lens will have an oblique power with sphere, cylinder, and axis, but instead of using this representation of power, we will use the power vector, which is given by 3 parameters, not quite this one, but 3 parameters, which are M is the mean sphere, J0 is the projection of cylinder over an horizontal axis, and G45 is the projection of cylinder on a 45-degree axis. Okay. Using this power vector, we can make a 3-dimensional representation in which each axis is one of these components, M, J0, and J45, and then each oblique power correspond to one point in this dioptric space. Okay, so the lens is represented by this cloud of points in dioptric space. At the center, we can see the user prescription that for this example is the target prescription is this one, 3 diopter sphere, 1 diopter cylinder, 45-degree axis. All the green points around it are represent oblique aberrations. Well, there is a threshold of 0.18 diopters determining whether the oblique aberration is noticeable or not. This threshold is represented in the optical space with this sphere with a radius of 0.18 diopters, and any point inside it won't produce any discernible blur. While the points outside the sphere will represent gazes for which blur is noticeable. Okay, and if we consider accommodation, then the effect of accommodation is a deformation of the sphere into this purple capsule, deformed along the vertical axis, which is the spherical component of the power. And once again, any point inside this capsule won't produce any discernible blur, and any point outside it will produce blur, noticeable blur. So let's compare 3 different lens designs for the same prescription that we are using in this example. This is a standard lens. This is a lens optimized with the previous digital ray path. And now this is a lens optimized with digital ray path 2. Let's see one of them in greater detail. This is the standard spherotorical lens, and we can see that the cloud of points corresponding to oblique power is very large. There are points separated by more than 2 diopters from the target point, and basically all the viewing directions are outside the region with non-discernible blur. In other words, for any oblique direction, direction, we will appreciate some blur in this lens design, and quite a lot of blur. This is the cloud point for the lens optimized with digital ray path, our previous technology. The number of points for which the blur is noticeable has been reduced. Now is 57%, which could seem a lot yet, but the point is that the cloud is much more compact. The amount of blur, although there are many points still with noticeable blur, but the amount of blur is much smaller than with a classical lens. And now the new technology, IoT Digital Ray Path 2, allows the cloud to shrink towards the vertical line passing through the target power. That means the astigmatism has been virtually removed, and we only have spherical error, but an amount of spherical error that can be compensated with accommodation. Only 0.5% of all the oblique directions are now outside this capsule. That means virtually all the field of view is virtually free from discernible blur. We can see this effect in classical maps in which we represent optical characteristics with respect to the Cartesian coordinates on the lens surface. This is once again the standard single vision lens, the previous technology, IoT technology, digital ray path, and the new technology, digital ray path 2. And we see that with a standard single vision lens, the blur goes above 2 diopters for a significant portion of the lens. These white isolines represent 0.25 and 0.44 diopters of blur. We can see that digital ray path makes a very good job in reducing this large blur, but still will have noticeable blur in a significant portion of the lens. Very small, but noticeable. And finally, with the new technology, IoT Digital Ray Path 2, virtually there is no noticeable blur at any point in the field of lens. And to finish, conclusions. IoT has developed a new technology that we call Digital Ray Path 2. Is our latest core technology in lens personalization, and it has two main features. It introduces user accommodation in lens optimization in a seamless and efficient way. The computation time has not increased in a significant way. Lens performance is optimized not just for a single object distance, but for all the wearer's accommodative space. There is a substantial reduction of oblique aberrations. For many prescriptions, there won't be any significant oblique error in all the field of view. And we have applied to a new product family, both single vision and progressive lenses. This technology will be available for a wide range of family of products. And that's all. Thank you for your attention.
Yeah, dear Dr. Alonso, I would like to thank you very much for your very interesting and informative lecture on IoT's new design. And I particularly liked the very clear and well-structured presentation. It was like a lecture at the university, so it was very informative. And I would like to thank you for this. Perfect. Anna, could you?
Of course. Thank you, Peter. Yeah, thank you, Mr. Alonso. I also like to thank you for your very interesting lecture. And yeah, I would like to start with two more general questions. So progressive lenses are becoming more and more individualized today. And at the same time, it is difficult to differentiate between the many major lenses, whether the visual performance has actually improved with each new generation of lenses. And therefore, I wanted to know for which presbyopic target group would you particularly recommend your concept? So which customers benefit most?
Yeah, you have to take into consideration that DRP2 is not a technology for progressive lens design. It's let's say it's a backbone technology for controlling or for better controlling oblique aberrations, which is a general tool that we have to apply to any type of lenses, progressive, single vision, or specific task lenses, whatever. Okay, so let's say it's a backbone technology for designing or for computing high performance lenses in a general way.
Okay.
It's true that the improvement in performance is not the same for all the users. It depends on the prescription. It works better, or in other words, it produces better results with hyperopes, with medium to high astigmatism, with large tilts in the frame. And it works better for people for not very high presbyopes, you know, for let's say 8 under 55. It already has some benefits above that age, but it's better. The benefits are higher or better for ages below 55. But it's a general concept. It's not intended. It's not intended for generating particular progressive designs.
Okay, thank you. So for single vision and progressives.
Yes.
Okay. And have you conducted also VERA trials on your user acceptance? And yeah, if so, what are the most important outcomes?
Yeah, a lot, a lot of trials. Yes, let me think about that. But we first made a trial with something like 20 testers comparing digital ray lenses, single vision lenses with digital ray path 2 against standard lenses. And the results were always equal or better. And when I mean better with a statistical significance. If for any task or performance metric or whatever, we don't get statistical performance, I'm ignoring the result. You may have better, equal, or slightly worse, but without statistical significance, we consider that as noise. So with the statistical significance, we got the digital ray path 2 better scoring in first impressions, which is the questionnaire we make when you try the lenses for the first time. After adaptation, in first impression, I think it was for distant vision. After adaptation, we got statistical significant improvements in 2 or 3 fields as overall vision, distance, and lateral vision. And in the guided subjective comparison, which is something we make for all the trials when the user has tested the 2 designs for a period of time, then they come to our office, and then we guide them through different visual tests in which they compare one lens against the other. Okay, this is something which is always done. This is our way to perform the trials, most of the trials. We make them compare the lenses in, let's say, in control environment. And in this guided comparison, the digital ray path 2 was better than standard lenses for all the visual tasks. Of course, this is comparison with the standard lenses in the typical base curves that manufacturers will select. We have also compared DRP2 against our previous technology, digital ray path, the first version of it. The improvements are not that much, but still there are significant improvements in both after adaptation and in the guided comparison. We have also tested digital ray path 2 with lenses having a little bit of accommodation, a little bit of addition for relaxing accommodation, not for presbyopes, but for either young presbyopes or even young people. Once again, the results were pretty much similar. And we see that we get the better benefits in the guided comparison, because in that environment, we ask the people to pay attention to lateral vision, which is the region in which they get the maximum improvement. Okay. And right now, we have also made comparisons with progressive lenses using digital ray path 2 as the background technology. But we have not yet finished studies using exactly the same progressive design. We have also changed the designs because we have recently launched a new set of progressive designs. And then we cannot say that the improvements comes from digital ray path 2, because there are also changes in the designs of the progressive lenses. So for progressive lenses, we have yet to test exactly the same design with digital ray path, the previous technology, and digital ray path 2. This is we are undergoing. These tests are under making.
Okay. Thank you. Yes, for the more detailed questions about the technology, I would like to hand over to Peter.
I have a question regarding the concept. As far as I understood, you reduce the oblique astigmatic error, and then you try to get a negative spherical error so that the eye can accommodate for this for this type of error. And because we only have two surfaces on the lens, we cannot minimize both errors simultaneously. So your decision is to reduce the astigmatic error, but this is a concept I know from Moritz von Rohr, who worked for Zeiss in the beginning of the 20th century. He invented a single vision lens series called punctal, where the astigmatic error at round about 30 degrees was more or less reduced to zero. Just with and they at that time they had no aspheric surfaces, so he used the typical churning approach in order to get or to choose the right base curve. Can you explain what the difference of your concept is compared to this more or less 110 years old concept of Moritz von Rohr?
Yeah, yeah. I think comparing a modern, not just DRP2, but modern lens design with Moritz von Rohr's, it's like comparing a modern freeform generator with a 19th century lathe. The concept is more or less the same. You rotate a part, you use a moving tool to remove material, but of course the technology is vastly different. Yeah, first of all, we don't try to reduce oblique astigmatism. This is not our goal, our mathematical goal. Our goal is exactly the same as in digital ray path, our first version, is reducing the blur, the overall blur, which is just computed, very simple, as the norm or the length of the oblique power error. Okay.
So the spherical error is included.
Is included. Okay. This is our
our
merit function.
Weighted. Spherical and astigmatic error are weighted against each other, so you measure the distance of the vector.
Exactly.
Okay. Okay.
Exactly. The distance of this vector of the oblique error, including both the spherical component and the cylindrical component, is what we minimize. The point is that we are considering in the RP2 that in those cases, it is not that we intend to make the spherical error negative. It can be turn out to be negative or positive. That depends on the base curve and the prescription and the object distance. In those cases in which the negative error is negative or well, positive, depending on the sign you defined it, and you can use some amount of accommodation, we take that into account. The point is that you reduce the tension in the merit function, because if you try to make astigmatism 0, you can see that in many cases, for some prescription and for some situations, the spherical error grows very high, well over 1 diopter.
Yes.
So the point is that just by allowing the spherical error not being compensated all the time, in those cases in which you can accommodate a little bit and not just accommodate, not just increase in accommodation, but also relax in accommodation when the object, when the fixation object is at a finite distance, when you are already using accommodation. So by taking this into consideration, you relax the mathematical stress, let's say, of the merit function, and get significant improvements. And also we are optimizing the lens, not just for a constant object distance, but for a potentially variable object distance. So, for example, for some cases, the blur that we get with digital ray path 2 can be worse than the blur that we get from digital ray path, the first implementation. But the point is that we manage to make the blur always below some threshold, the threshold that we consider is going to be negligible to the user. In our previous implementation, the merit function tried to zero the blur. And we think this implementation is much better.
So the blur can be mathematically higher, but well within a certain range that is not perceived by the wearer as a disturbing kind of blur.
Exactly.
Is that right? Okay. So I understand you're using a much more flexible concept than in these old days and in your first version of digital ray path.
Yeah, exactly.
I had a second question I have a second question regarding the binocular properties of your new lens, but as I understand now, maybe you you really avoid the problem. But let me ask it anyway. If you look straight ahead at a distant object, and now you move your eyes to the left or to the right, and you get a negative error by when viewing through the lens, the wearer has to accommodate if he or she wants to see a sharp image, and we all know that accommodation and convergence are coupled in a not very fixed way, but in a loose way, and so if you accommodate, you will have a problem looking at distant objects, and so you have to learn how to look through these lenses. Is that true for your concept, and does it explain why you told us there is a learning phase, and after the adaptation your results are much better? Is that correct, or
no, not really, because the it's quite automatic, the user response. The point is that you have to take into consideration positive and negative relative accommodation, not just the let's say the overall accommodation. For one fixation point at some distance, you need some accommodation level. And the point is that you may change a little bit the amount of accommodation but still keeping the convergence constant on your fixation point. And this amount of positive and negative accommodation, which are called relative accommodation, can be measured. There are some maximum levels above which both negative and positive, you cannot keep binocular vision, or you just simply lose the focus. But what we do in Digital RayPath 2 is by looking into the clinical data, using an amount of either positive or relative accommodation that we know is well within the comfort region. And the interesting thing is that a small amount of correction from this relative accommodation makes a long way in improving the overall amount of blur in the whole lens, in the whole field of view. It's just very interesting, just allowing 0.25 diopters, for example, because this can change from point to point or from, depending on the data you have from the customer. Just 0.25 diopters makes a long way in reducing the overall blur of the lens. This problem of, for example, having very small astigmatism, very large spherical error at some regions of the lens in the peripheral area usually. So the key idea is using relative accommodation, but well within the clinical published data on what are the comfort levels for this relative accommodation. There is an interesting development by Yamahaki. There's an interesting pattern in which they use a complex model to infer the relative accommodation from Peter's data on visual acuity. But this cumbersome. We think it's a better approach, a more simple approach to use clinical data to fix some threshold that we know that we cannot surpass in order to have a comfort lens. And also you have to take into account that oblique aberration will occur in the periphery of the lens, where you are not going to be looking steadily, with the exception of the near region of a progressive lens. So this will give you a better overall vision, but you don't need to focus continuously in an oblique direction. So you will need this accommodation just for small amounts of time.
Yes, that's right. Yes. And one last question I have. So you're using clinical data for determining the thresholds, but I know from literature that regarding blur, this is a very individual thing, and some people accept more blur and others don't accept any blur, but it's almost, it seems for me almost impossible to do it right for all types of persons. How do you manage this in your new concept?
Yeah, this is there are different aspects here. For example, if you consider just the tolerance to blur, well, this is something you will need an extra customization parameter to take this into consideration. We are using right now 0.28 diopter. This is our threshold for considering that the blur is not.
It's a very small value, acceptable for more than 90% of.
Yes.
Okay. Thank you very much.
You're welcome.
For this interesting discussion, and I think we could shed some more light into the concept. It seems to be a very good and very flexible new approach, and I hope it will give you give you the response from the market as well.
Let's hope.
Yeah, that's the reason why we develop lenses.
Yeah, we're really getting a wonderful feedback from our customers, mainly from United States, because this is the first place where we started selling the lenses, but now from Europe as well. And we're getting very, very good feedback from our customers, so we're happy.
Yeah, thank you.
That sounds good. Yeah, then I'd like to thank you, Mr. Alonso. It was really interesting, your lecture, but also your answers to Peter's questions. I'd like to thank you, Peter, for your time and your interesting technical questions. Yeah.
Thank you all. Thank you all. You're very welcome.